So I'm Craig Douglas. I'm the third author on this talk. Clay Carper and Aaron McClellan are graduate students in the computer science department at the University of Wyoming, and I have been advising them on a project. So today, thanks to the invitation kindly given by the organizers of the IMECS conference in Hong Kong, I'm going to talk about a support vector machine model for predicting closures on Interstate 80. So Interstate 80 is one of the major highways in the United States. It runs from San Francisco on the West Coast to Teaneck, New Jersey, which is just across the Hudson River from New York City, so on the East Coast. The total length of the highway is approximately 3,000 miles, and the highway runs from roughly sea level on both the east and the west ends, all the way to 8,640 feet above sea level, just east of Laramie, Wyoming, which is where the University of Wyoming sits. So the motivation for this project came because Clay Carper, the first author, commuted between Cheyenne and Laramie for an entire academic year at one point. In order to get between the two towns, Cheyenne is 6,000 feet above sea level. Laramie is 7,200 feet above sea level, and you have to go up to 8,640 feet above sea level. This is the only direct paved route between the two towns. There are some other routes that are not paved, but you're not likely to commute on those roads. The span is not terribly long. It's roughly 51 miles. The speed limit is 75 miles an hour. It is very common to see 18-wheel trucks driving either 50 miles an hour or 90 miles an hour, however, on this. We have a very strange climate that you have to deal with. The roadways are frequently quite hazardous due to winter weather conditions, and it can snow all 12 months of the year and cause road closures on any given day of the year. Okay, today is July 5th, and yesterday, July 4th, I-80 closed for several hours due to a snowstorm. So 2 or 3 times a year, we get a big pileup in that stretch of the highway. By big pileup, it involves at least 100 vehicles. There may be fatalities. Usually they're not, because when these pileups start, as you can see, there's ice and snow on the highway. And in general, vehicles are not moving very fast. They just can't stop. So the maximum elevation change between Laramie and Cheyenne is roughly 1 kilometer. And as I said before, you can have snow possibly any day and certainly any month of the year. 2018, we had 2 days of closure in July, a day in August. 2019, we had 3 days of closures in October. Yesterday, in 2023, we had a closure in July. The primary reason the highways closed is to minimize these large accidents. Okay, the closures are typically based on ice, snow, and or fog. We can have fog any day in the summertime, for which you can only see not very many meters in front of your vehicle and you're going 75 miles an hour, which is well over 100 kilometers per hour. The closures can be of completely unpredictable periods of time. Often the road closes after it should close and reopens long after it should be reopened. While it's closed, the Wyoming Department of Transportation typically gets trucks out to clear the road of ice and snow. The technique used by the Department of Transportation is not based on science, modeling, or computer predictions. It's based on observing cameras along the highway and people making decisions in the basement of a building in Cheyenne. The predictions that the Department of Transportation makes itself tend to be what I would consider severely lacking in science. They have sensors on the highway that they do not have hooked up to computer models in order to scientifically do a better job. However, the Department of Transportation keeps track of the closures, and this data is publicly available to researchers. It's very easy to register and get access to the data. They have apps for both Apple and Android-based phones called Wyoming 511. This app, unfortunately, has no predictive capabilities. It's very frustrating to use. Most people, within 2 weeks of putting it on their cell phone, delete the application because they've found it worthless. So what kind of data is available from the Wyoming Department of Transportation? There's weather-related closures, which includes dates and times. There's ad hoc closures, which are not weather-related, but have something to do with other features, such as a major accident along the highway. Once again, dates and times are available. The closure information is not 100% accurate. The times listed for closing and opening of the highways is not necessarily to the minute what actually happened. There is other data, which oddly enough is hosted not in the state of Wyoming or at the University of Wyoming, but through a spin-off company that's based out of the University of Utah's Department of Atmospheric Sciences. This data involves 29 individual quantities based on sensor measurements. The sensors are scattered along I-80. The sensors have been put into the roadway or next to the roadway over an extended period of time, and the quality of the sensors varies rather noticeably based on when the sensors were installed. So the more recent sensors are more accurate and have more data items that they're collecting. Not much of this data is actually available to the public. A lot of this data, however, is available to researchers if you can convince MesoWest to actually give you the data. In theory, you can buy the data. In practice, they may not sell it to you, but might provide it to you for free. And they might provide it to you for a period of time, and then suddenly it stops coming. So it's somewhat unreliable. And the Wyoming Department of Transportation has the same problems that my research group has getting the data out of MesoWest, even though the data is technically owned by the state of Wyoming. So we have 33 possible pieces of data from any given location. At many of the locations where the data is collected, we do not have all 33, however. Of the 33, there is 6 minimal sensor parameters that we need: the air temperature, the relative humidity, the wind speed, wind gust information, visibility, which is in terms of miles you can see, the dew point. So the air temperature and relative humidity is actually available from every sensor along the highway. However, there is missing data from time to time because the sensor doesn't provide it necessarily reliably. And in the case of missing data, what gets substituted when cleaning up the data sets is a medium of all the data points at roughly the same time in the same region. The air temperature is given in Fahrenheit. You could convert it to centigrade easily enough. The relative humidity is measured as its own unit. The wind speed and wind gust is highly necessary because here in Wyoming, high and gusty winds are very common. They occur frequently during certain periods of the day, particularly late afternoon and early evening, frequently also in the mornings to lunchtime. And both the high wind and gusty winds are extremely common for almost any severe weather events, thanks to the way air tends to move around mountains. There is an associated high temperature set of differentials. The wind is recorded in miles per hour. Once again, converting it to kilometers per hour is trivial. The wind gusts are recorded only if the gusts exceed 10 miles an hour. So for 2 months in the fall and 2 months in the spring, in the late afternoon and early evening, it is quite common for the gusts to exceed 75 miles an hour. That's well over 100 kilometers an hour. And it will do that for 2 or 3 hours during each day. When wind speeds are missing, once again, that gets replaced by the median of the data at nearby sensors. When wind gust data is missing, it's replaced by 0 and normally indicates that the speed is less than 10 miles an hour rather than just a sensor failure. The visibility and dew point is present in almost all of the sensor readings. There are some sensors that do not provide this information, but they tend to be very old sensors and there are newer ones typically nearby. So typically, the visibility is measured between 0 and 10 miles. In the data, if 10 miles is the data that indicates that there is no visible impairment anywhere near that sensor. Typically, you can't see for 10 miles because of the terrain elevation changes, but if you could see, that's how far you could see. The dew point represents the atmospheric temperature where water droplets condense to form dew. Missing visibilities typically are replaced with a 0 quantity, assuming that that's similar to nearby associated variables. Missing dew point values are replaced with the local median. So you could ask, why only use 6 variables? So part of it is that for a number of the fields, the data is actually sparse. Many of the sensors just don't provide the data. There's a lot of irrelevant data. For example, there is a collection of data that is dealing with high temperatures, particularly the heat index. A high heat index is never a cause for closure, which means it's irrelevant. There are some pieces of data like the weather condition, which is a character string. The terms are somewhat vague and don't actually provide a useful numeric potential piece of data to go along with it. So in fact, we ignore it. We have experimented with converting the string data to numeric values that might be helpful, but we found that among the other 6 variables that we care about, that the string data actually is easily replaced. So in this slide is a little bit more specific about why we rejected the weather condition data, but in point of fact, what I just explained is more than adequate. You can read this slide if you want for details, but I've already explained why we rejected that data. So what about the data properties? Not all the data is consistent. Some of it is inconsistent. The variables we used were selected based on several criteria. One is availability, another is non-sparseness, a third is relevance, and a fourth is numerical accuracy. We didn't just pick these out of the air. We not only saw the logic in these, but we also did statistical investigations to find which of the variables seemed to be most useful to our study. So sensor density, as it turns out, is now adequate along the highway. There was a very large number of sensors added after 2015 along the highway. The goal was to be able to collect enough data to eventually start scientifically projecting when to open and close the highway. And our study shows that, in fact, they do have enough data to do this just based on data, not based on looking out a window or at a camera. So we have 2 sets of data. The Wyoming Department of Transportation data set is clean, it's fully contained in one file, so one data set. The Meso West data set, on the other hand, is the raw data. It has to be fixed before it's useful, and it comes in 41 Excel comma-separated variable files. So we have to take both sets of data, clean them up into a single combined database in order to actually do any useful work for predictions. So we ended up using MongoDB. This has all the capabilities that we would like to have. Minimal pre-processing is required, and we could get MongoDB to produce one brand new comma-separated variable file for everything that we want out of the 42 data sets. So cleaning the Meso West sensor data, we used Python and NumPy and Pandas. Provides all the tools that we need. It's simple to program. It's not the fastest on the planet. If we'd used something like C, Fortran, C++, it would have been quicker. On the other hand, the Python code is relatively straightforward. It's easy to maintain. And this is not something that you run on a daily basis, something you run every now and then when you get a lot more data in-house. So the procedure is simply import the sensor data, eliminate any of the sparse or undesirable parameters. There are a collection of missing or not a number data values, and we have to replace those using whatever the appropriate method is. There may be a set value like 0 or a median of local data, and then we export the clean data as a CSV file. So the advantages of Python include that you can read the source data files instead of just altering the source data files. So we can actually experiment with different ways of cleaning the data up without altering the raw data files that we receive from Meso-West. The Python procedures works with the data sets, particularly the 41 data sets we get from Meso-West are each relatively small, and we can do the cleanup inside of main memory of the kind of computers we have. Python lets you do concatenation and quick replacements, and we can export the files in a number of different file types, which has allowed us both flexibility and the ability to do a number of different types of experimentation before coming up with a set system. So the entire data set is actually relatively small. It's about 1 gigabyte for a year's worth of data. We're not going to train on the whole data set because that's a little large and overkill for what we're doing. If we work with the entire gigabyte data as a training set, the computational time gets to be fairly significant. The closure feature is also completely lost if you work with the whole data set, because it's roughly 1% of the overall data. We work with the whole data, we're going to have an overtrained set, and that's going to give us an absolutely terrible model to work with. So we had to come up with subsets of the data. And we had to first investigate the data sets to find subsets where the closure and open road conditions contain similar quantities. So some months turn out to be much better than other months. So for example, November, which is winter here, has pretty consistent closure and open road data. While if we look at May, in the first half of the month, it's still winter here. It's still snowing on a regular basis. But in the latter half of May, we might have spring, depending on the year. And so the variations between the first half of May and the second half of May can be quite considerable and don't provide particularly good data for training sets, as it turns out. All right. Initially, to get a single data set, there wasn't enough experience to do this automatically. So it was actually done manually using Microsoft Access. In the process of doing the manual cleanup job, a collection of scripts were developed that automates this when adding new data. Okay, so we're interested in looking at a support vector machine approach to this. You could also use a neural network or convolution neural network type approach. Both have been studied, in fact. So a support vector machine is actually an adaptation of the earlier concept of a perceptron. So perceptrons are based on what's in your brain. It's trying to emulate a single biological neuron in your brain. You may have multiple inputs, but the output is either, yes, there's a signal, which is a 1 on the computer, or no signal, which is a 0 on the computer. So you end up with a linear binary classifier, which in fact is not actually binary, but trinary, because there's an error term. So normally you get a plus or a minus 1 based on a weighting vector transposed inner product, well, the weighting vector inner product with your input vector x. It's greater than 0, you have a signal. If it's less than 0, you have no signal. And if the weighting equals 0, this is an error term. So in theory, you should never get this 0 if your data is appropriate. And so in that case, it is truly binary. So there are a number of perceptron issues with the basic algorithm. Sometimes when you're trying to create this separator to get the plus and minus 1s, no such hyperplane separator exists. And so you're going to have mistakes. When you have new data, which is represented in the second figure with a question mark, you actually don't know which side of the hyperplane separator it really should be, because the perceptron algorithm converges as soon as it finds any hyperplane separator separating the data. All right, so support vector machines were developed to get around the problem, some of the problems perceptrons have. In particular, the SVM algorithm chooses a hyperplane separator that maximizes the margin between the points in the training set. So this is a supervised learning algorithm, meaning the output is known for some labeled test set. So the idea is to get a separator, such as the red line in the picture on this slide. That maximizes the difference. So you want to compute a weight vector W and a value B in order to find the maximum margin, which is represented by the inner product of W and X minus B is 0. The actual offset from the origin along the normal vector W is just the value B over the L2 norm of W. And if the weight is not normalized, you can normalize it easily enough by just rescaling W to be W over the L2 norm of W. So the actual distance between the two hyperplanes that separate the data in this case is 2 over the L2 norm of W. Okay, and that value is what we want to minimize. So we can set up a constrained optimization problem. The L2 norm of W has a square root in it if you look at the mathematical definition. So this makes creating a linear optimization problem quite difficult. And in fact, what people do is construct a quadratic optimization problem where you look at the square of the L2 norm of W in the formulation. And that simplifies the calculation noticeably mathematically, but computationally is more expensive. So we actually constructed a linear support vector machine, or LSVM. It's similar to a support vector machine. In our case, we end up with an output that's going to be some y hat that's either 0 or 1. where 1 represents a closure and 0 represents an open road. And when we're computing the weight vector and the scalar b, we run our optimization algorithm to a tolerance of 10 to the minus 10th. So we actually implement this using Python's scikit-learn package, which uses optimized C code. We find some sort of minimal weight vector W that maximizes the distance between the instances in our data set, and which should result in strong predictions. The actual way you do this is you set both all the elements of W and the scalar B to be 1, and you loop until convergence, updating the weight vector W using the algorithm on this page. And when you're done, you end up with the scalar value B being equal to 1 over the number of support vectors times the sum of the computed weight vector W inner product with each of the x sub i's minus y sub i's, where the x sub i's are known test data with known labels. All right, so we used cross-validation in order to evaluate the accuracy of a given training set. This separates the training set into a collection of random subsets that are known as folds. If we have k of these folds, the algorithm is trained on a subset of the folds. The folds that we do not use in the training sets are used as test sets. So the scoring is based on the percentage of correct predictions on each of the test sets. All right, so on our data that we actually used, we tried 3, 5, and 7 sets for generating the model. The mean accuracy with 3-fold sets was about 68.5%, 71% for 5 sets, and 70% for 7 sets. So just taking this, no cleanups, no boosting, no playing further games, the accuracy of the model was about 71%. Now, if you come from computer science where you can get all the accurate data in the world you like, many people say, well, if you don't get 98%, 95%, you're wasting everybody's time. This is real data. It's got real problems. Under the assumption that this data set is linearly separable, this is a desirable accuracy, even if it's a bit disappointing. All right, but I'm giving you a hint. We can do a lot better than 71%. So we can look at hyperparameter optimization. In this case, we have a penalty parameter of the error term, which we'll call C. Initially, we start out assuming C is 1. We use the cross-validation process to vary the value of C. And regardless of the value of C, the errors we got from cross-validation were within about 1% of each other, which is well within the variational norms that we might expect. So what it says is our accuracy on a first attempt is 70 to 72%, which matches our k-fold analysis. All right, so we first looked at some boosting algorithms. So boosting algorithms improve the predictive accuracy without changing the models using what's called a boosting algorithm. So we use the eta boost algorithm, for which there is an implementation in the scikit-learn library in Python, and is one of the boosting algorithms that's in that library. Okay, so this fits additional copies of the input data with altered weights with respect to incorrectly classified data in order to try and improve the overall algorithm. Okay, so we had n estimators, and we start generating boosting data based on the estimators until the AdaBoost algorithm terminates. And in particular, if the fit of the estimators turns out to be perfect with respect to the data, then the algorithm automatically terminates. Otherwise, it terminates when you reach the maximum number specified of estimators. So, using the same number of linear support vector models as data points, the approximately accuracy was increased to 80.65% versus 71.2%. So this is roughly a 13.25% improvement. The accuracy above 80% is clearly more desirable than 71%. So given the current training sets that we have, 81% is about as good as we can get. However, we did better. So we looked at a confusion matrix overview to get some insight into what the algorithm was doing. We looked at two confusion matrices, one for the standard model, one for the boosted model. And we used cross-validation as the evaluation metric for computing the confusion matrices. And we looked at this. What we can see is what the true negatives and false negatives and positives are for each of the cases. And what we can see is that the boosted algorithm, as expected, is doing better. All right. So let me conclude that this LSVM approach turned out to be quite good at predicting when I-80 should close, and also quite good at opening. So the boosting gave us a significant increase in predictive capability. So what's not in here is work that's been done quite recently, and that is we found a better way of doing boosting, and we've collected more data as time has progressed. And what we're up to now is a little over 90% accuracy. So now we're getting close to the computer science. Oh, this is what you should be able to get type of quality of the model. One of the features we would like to add, which requires help from the State Department of Transportation, is to be able to include new data in real time to update the model in an accurate way. We would like to get the Wyoming Department of Transportation to vastly modify their Wyoming 511 app in order to use our research. Whether that will occur or not remains to be seen, however. We can do much better than they can on predicting when to open and close the highway, however. So with luck, we'll be able to convince them to use our work. And with that, I'm going to say thank you for watching this talk, and I hope you found something useful in it.